Today we will do an experiment to test the electrolytic capacitor leak current. Same thing, the DC power is from the amplifier, and senior amplifier is 44.5 volt from the main power supply. There is a switch here. I put the current meter over here. This is A meter, because I don't want this thing to handle too much current. When the capacitor charging, the current will be much bigger than this thing can handle. So I put it parallel to the switch. When I do the normal charge, I turn this thing on to bypass this meter. After this thing got full charge, I switch this thing to off. This current meter will measure the current when this thing is full charge. We can concern about this is the leak current for this capacitor. If this leak current is within the specific of the capacitor in the certain voltage, because we are using this thing in an amplifier, so this is the real voltage we will use it. So it's much reliable than we just using some small multimeter or something to test that. So this is the color. This is the circuit we're gonna use to test this capacitor. Let's go back to the circuit to make a double check. 44.6, and we double check the voltage in the capacitor. 44.0. There's something drop in between the provided voltage to this capacitor. Definitely it will come from the resistor. Here we see the resistor have like a 0.5 volt. We are connected this voltmeter parallel to the capacitor right now. This voltmeter maybe draw some current from the circuit. Let's take this thing out to see what happens. The feeding voltage still 44.6. Let's see the drop. We don't see voltage in this this resistance. Also, double check the voltage in the capacitor. It rises to 44.6. We believe right now the capacitor is full charge. If we still have current follow in this circuit, we can think of it as a leak current. Let's turn off the switch to put this thing into the circuit to see what is the current flow in here. We can see there is a current about 2 to 5 μA, sometimes even go to the other direction. Let's talk a little bit about this circuit. The DC voltage provided from the amplifier. This is a Sanyo 2050 amplifier. It can provide 44 volt from the main power supply, and this voltage pass through a regulator, drop to 34 volt over here, 34 volt. Let's start to do some real tests. I chain this 4 capacitors together because it's easy to charge. I connect all the negative lead together, and the positive lead is separated right now. The first two, these two, are 50 volt 220 megafarad. The next two are 50 volt 330 megafarad. Right now we are using the first one. I'm using the first one to do the testing. Once we turn the switch off, this current can follow through that meter. Let's try that. Yeah, we see that. Let's push that into. We see there is about 3 μA current. Also, right now in this circuit, only thing we have is the capacitor. This thing's cut off already, and go all the way to this thing. So we can say all the current we measure over here is the current goes through the capacitor. I think we can say this is the leakage of the capacitor. Now I switch to the other one, the second one. Let's go to the ammeter. We see that it starts from the 10 μA. Right now it looks like it slowly drop. Slowly drop. Very slow drop. See that right now it's 5 μA. It's still dropping. After another minute, see that thing is dropped almost to the 3 μA now. Why it dropped? It's because this capacitor is out there for very long time. Nobody use it. No voltage applied to that. When you put the voltage on that, the material inside of the capacitor is start to heal itself. The capacitor have a self-heal, that kind of function. When you apply the voltage slowly to that, it heals itself. The healing, we call that foaming. The foaming process take about an hour to fully foaming. Then in this real time, we can see that current already dropped from about 10 μA to now is 3 μA exactly. 3 μA. I don't want to say exactly how many μA because this meter is not 100% accurate, but in this process we really see something is what the old capacitor we took out from the 3-4 decades ago, the amplifier, and it got very little leakage. And also we know there is a foaming process when you apply to the capacitor if it is out of the circuit for a long time. Yeah, it is foaming. And now I move it to the third one. It is 50 volt, 330 microfarad. And this one is a little bit bigger than the other one. The rest of the two. These two are 50 volt, 220. Actually, it is a 50 volt capacitor. We apply 34 volt to that. A little bit low, but usually in the real equipment, they are not using the full voltage of the as the label value. They always have a little bit redundant. For now, let's try to take this thing off to see the current. Here we see the current is slowly rising a little bit. Now the current is about 3.5 mA to 3 mA, that kind of range. Yeah, this capacitor look like it's stable on the 3 mA, that kind of range. Let's try to see the other one. Before that, I have to turn this thing off and I disconnect this one. Put this here and start to charge this one. Let me see what the voltage it is. It is about full charge because I already charged them in the circuit for half hour. Let's slowly turn off this thing. Yeah, we can see the current go up to 6 mA. And I see this thing is dropping. It's foaming. After a couple minutes, come back to see what the current it is. It actually dropped to about 1 mA. It's kind of a very low leakage for this capacitor. Is this current is good? I don't know. I got some, see this 50 volt 220 microfarad niche capacitor from Mouser. It is new capacitor. See the size. You're sure it's a different brand and different a different model, but it's still the size, the modern technology make that capacitor much smaller than the one. I believe this thing we can call it grandfather. I connect the new capacitor to the circuit and we charge it to the full charge. Let's remove the voltmeter and turn off the switch. Let's read the current. Yeah, the current is around 2.5 milliamp and dropping. It's still dropping. It kind of the foaming. Yeah, it dropped to 2 milliamp. By this kind of a reading, we can see the new capacitor have like a similar leak current to the grandfather one. It's about 3-4 decades ago, this old one. But for this testing, we've put 35 volt on that, 34 volt on that. The capacitor is 50 volt on the label. So if we want to make sure it is really working on the 50 volt or 40 something volt, we probably needed to double check with the same voltage. But for this experiment, I think that we already know this old capacitor is still have very little leaking. Let's go back to the ammeter. You see, the new one, the current already dropped close to 1 mA. Yeah, that's the minimum thing we can read by this equipment. I don't know. We have to go back to the chart. There is a chart for the capacitor leak current. We need to go back to there to compare the leak current to that to see that within the specific. I think for the Nichicon they have the leak current is after you apply the voltage for 5 minutes, and you need to have like the leak current less than the capacitance times the voltage of the label square root times 3. And it's about like 2 milliamp kind of a range. By that, but I'm not quite 100% sure, but by that kind of remember, I always say this capacitor, the new one, the old one, they are all good. Let's go for the other one with a little bit bigger value. This one is a 35 volt, 1000 microfarad, also Nichicon, new. The voltage charge already 33.5 volt. It's because this voltmeter here. Let's take the voltmeter out. Okay. Now turn this switch off. See the current. Now see the current is right up. And after you lower to like a 15 mA, it starts to drop. It's dropping. Even though it is a new capacitor, because you already sit on the shelf for a minimum a year, right? So it starts to foaming, dropping. The current is dropping. Let's wait for a couple minutes to come back to see how is the final current it has. Now we come back half hour later. Let's see that current. Now it's about less than 2.5 mA. Less than 2.5 mA for this new 35 volt 1000 microfarad Nichicon. We will compare this one to the 50 volt 1000 microfarad. I think it's about over 35 years old. I took this thing out from one of the net 7400 net 7400 amplifier. Now we put the old capacitor into the circuit. It is full charge. Let's now measure the current in the circuit. It's barely moving. The meter is barely moving. Let's turn it off to see. See that? It's barely moving. I don't even be able to measure what is the leak current it is. It's so small. If this capacitor still working, still charging and hold the value, I think it is pretty good. We probably needed to double check to see what is the capacitor it is. I put the capacitor into the D5000 to double check the capacitance. With 120 Hz frequency testing, the device reading is 641 microfarad. Let's double check the ESR to see what it says. The ESR is 0.5 ohm. 641 compared to 1,000, it is lost half of the capacitance. Wow, that's very dramatic change. It doesn't matter what is the leakage you have, but you already lost half of the capacitance. So yeah, when I replace this capacitor, I just close my eye to do that. I didn't test it, but I believe I did right. Now we go for the new one, the same 1,000. With the reading in 120 Hz is 938. Oh yeah, that's pretty close. Let's see the ESR. ESR is 0.1 ohm. Remember the other one is 0.5 ohm. ESR has something to do with the aging, because it indicates something inside the capacitor is running dry. After it's running dry, the ESR value is going up. So by this testing, we can roughly say this new capacitor is much healthy than the one very old. Yeah, I never know this can be that bad. Now it made me go back to test this old capacitor also. When we do the leak testing, they are all similar to the new one. The leak is so small. Let's do the double check of the capacitance. This side, this two is 330. This two is 220. Let's see the capacitance of each one. I connect the negative lead each together already. So now I just need to switch the positive lead. Now it's the one on the left. 330. Yep, it read 330 for that capacitor. And the ESR is 0.1 ohm. Look pretty good. Let's switch that to the second one. It takes some time to read it. 331, same ESR. Yeah, good. Third one, 220. Reading 244.2, higher than the label value. It doesn't make any difference, because capacitor always has at least 20% of the tolerance. So it's not surprised it go a little bit up. So this 220 reading 244 and the ESR is 0.1. It's almost like okay. Let's go to the last one, 220. Reading 234, ESR 0.1. Yeah. This green guy, Nichkan, good. 40 years old, still like this healthy. This remind me, in the internet, somebody say, as long as you see those light blue capacitor in the amplifier, replace them. I think it doesn't make some sense to my real test. Somebody actually learned this class in a hard way, maybe. Let's try a bigger one. 42 volt, 6800. It is from, I don't remember which amplifier it is. It's the old amplifier. Let's charge it. Now this capacitor is full charge, and I let it form about an hour. Let's see what is the current. We need to switch that thing off. Let's switch it on and off. We can see in that 34 volt, it got very little leaking. I put this 42 volt 6800 microfarad capacitor in the DE 5000. The reading is 3000 microfarad. It kind of lost at least half of the capacitance. I'm not sure it is because the device not accurate or is actually lost that much. Let's test another new capacitor to check the device. This is a 4700 microfarad 35 volt new Nichkan. Let me put it in the testing. The reading is 4000 microfarad and the ESR is 0, kind of very low. Yeah, for this new one, 4700 compared to this 6800, this reading is 4000 and this one reading is 3000. Definitely this guy has some problem. Let's do a real test. I don't quite believe that DE 5000 say this guy dropped to 3000. I don't know. We do a real test. Right now, 34 volt here. If we charge to 1 tau, 34 volt times 3.2% equal 21.5 volt. So if we charge this capacitor to 21.5 volt and then we stop this watch to see how long it takes to charge this capacitor, and then we put this guy here to see what's the comparison. Okay, now we needed to discharge it, make it to 0. Okay, now I'm gonna start the charge and start the clock. Now the voltage is rising up. We will stop at 21.5 volt. Okay, now I stopped at 21.5 volt is 34. Make a note. Say the 6842 volt. This guy get a 34 second 25. This is the time. So this equal to tau, right? We don't do the calculation because calculation doesn't mean anything to us. We take this thing out. Now we put the 4700 35 volt new capacitor back to the circuit. Reset the clock. Discharge it. Make it to 0. Now we started charging and start the clock to see how long it takes this guy to charge to 21.5 volt. We stop the clock right at the 21.5 volt. You got the reading is 23.15. This is the tau for the server 4700 35 volt. This capacitor. We are not calculating the RC anything. We will do the math using this ratio. We will not using any theory to calculate that. Just do the 34.25 by 23.15. You will equal X 4700. Now, by this equation, X will be equal 34.25 divided by 23.15 times 4700. This gonna be estimate how big the capacitor is. Let's go to the calculator. We do the 34 times 25 divided by 23.15 equal this times by 4700 equal, we got 6953. The result over here is 6953. I don't know if this number is actually the capacitance of this guy, but because we are charging that by the real electricity, real resistance, and the real time we count that. By the time they both reach 21.5 volt, this one take 34 seconds, and this one take 23 seconds. I would believe this capacitor actually have more capacitance than this one. It's not like the DE5000. Say this guy have 3000 microfarad and this guy have 4700 microfarad. I don't know, maybe the other parameter take a effect of the result of that handheld device. To double check, to make a fair comparison, I put another one, 50 volt, 10,000 microfarad, to do the calculation also. Let's discharge this guy. To 0, and now we start charging. Okay, now stop at 21.5. We get 50 seconds. That's 0.4. I don't even try to use it. Now we put it in the same equation. Put in the same equation. X equal, this still the same, 34.25. This become 50. It's a 50 seconds, we just test it. And right now, the tester capacitor become like a 10,000 microfarad. Let's do the calculation to that, to see if that make any sense to us. So we get 34.25, and we times the 140, right? And we divide by 50. 6850. The result 6850. Both of this testing, we are confirmed this capacitor is still get close to 6800 microfarad, this kind of a capacitor. Because we compare this guy and this, all three. So get the ratio. I would believe this, in this voltage, 34 volt charge, it hold its value as this label. Because the DE5000, the DE5000, the voltage, when this guy testing, it only got like a 9 volt battery inside. So if this value is more meaning than the real test, I don't know. But if I put this capacitor into my amplifier, it will work in this voltage, not the one in the DE5000. So I almost believe this is the one. This result is, I will trust this more than the small device. One step over to see it. I used the 4700 microfarad, the time 23.15, put it here. And I'm using the 10,000, that one, 50 second. And after the calculation, I get this value compared to the 4700. It's pretty close. So I will say this calculation means something. It does mean something. It means the real world capacitance. Let's do something usually we're not supposed to do that way. I got see this one. Not sure you can see the label. 16 volt, 33 microfarad, 16 volt. So we know we already have like 34 volt on this circuit. Let's put this in. Let's connect this capacitor to the circuit. Before I do that, I need to have something here. See that? Put this thing on. I don't know that thing is like a grenade or just a small pop or nothing happened, but safety first. Now let's connect this to that. Watch that meter. Yeah, it jumped up. Now it got 0.8, 0.7. Now also when we look at the voltage, it shows 30.7 on this 16 volt capacitor. We're using 34 volt. We got 0.6 milliamp current. We know this one take about 0.4 to 0.5. Let's take it out. Now we can see in the ammeter we got about 2 milliamp to 3 milliamp. This thing won't be able to measure that detail, but we can see it is about 2 to 3 milliamp. That means leakage current based on this thing from 16 volt, supposed to be 16 volt used, but we apply 34 volt to that. Sure, there is something dropped from here. It's not purely 34 volt. It might be like 31 volt to 32 volt. But actually, right now we have leak current is 2 milliamp. 2 milliamp for this small thing, and compared to this one 50 volt, and have no leakage current. I think this one is not supposed to use that way. We lucky it's not explode or something. Let's go one step further. Yeah, this one. 6.3 100 microfarad, 6.3 volt. I still have my goggle, so I will try that. Connect this thing to here. Watch the meter. I should put this thing in also. So right now we have 0.4. Now put this thing in. Well, you drop to 2 milliamp, 2.6 milliamp. We know that voltmeter take a 0.5, so it's actually 2.2 to 2.3 milliamp meter. So this guy have the lead current is 2.3 to 2.4 milliamp